Well, hello and welcome to the Bay Area Rust Meetup. My name is Yerki, and I'll be your host tonight. So we're very happy to have you here. And then for the first thing, you haven't done it, you can join our Discord server, and you'll be able to hang out with the other Rust enthusiasts in there and so on. But I guess then a lot of you have already done it, since I don't see a lot of people then trying to capture it with their phones.
Yep.
Okay. All right. All right. And before we start the talks, I just want to have a round of applause for our generous sponsors. This was sponsored by Z Industries and Root VC. And yeah, let's just give a round of applause for them. So this space is generously provided by Root VC, and I think Lee wants to give us some words of encouragement in the beginning.
Thank you. Hi, everyone. Lee Edwards, partner here at Root Ventures. Thanks for coming over to the West Bay to hang out with us. Root Ventures is 4 partners. We're all former engineers of different kinds. I'm the one with the software background. Chrissy comes from hardware. Avidan does sort of embedded systems, and Kane is kind of hard industry. And yeah, so we love hosting stuff like this. We've been big supporters of Rust. I think in my part of the portfolio, maybe around half of the companies are using some amount of Rust, and a good number are using a lot. So we were first investor in Zed, and we play around with it a bit. Yeah, you probably don't want to see as a 10-year Ruby developer, you don't want to see my Rust code, but super excited to have you all. Thanks for coming up.
Yeah. No, interesting.
All right, thank you. Okay, so tonight we will have 3 amazing speakers presenting to you about how they use Rust in their lives. And after that, we will have time to hang out in this space and mingle. So don't dash off right away. The first speaker is Taym Haddadi, who is the contributor to Servo. And Servo is the open source browser engine written in Rust. And if you don't know, the Servo actually was co-created with the Rust programming language. So this project is has a special place in the history of Rust as the programming language itself. So let's give the round of applause for Taym. And yeah, I just wanted to mention that Taym is actually based in Eindhoven, Netherlands, but he generously agreed to step in the middle of the night to give his talk to us. So the talk is going to be remote. So this is why it's important that you are able to actually then see this screen. All right. So again, let's give a round of applause for Taym.
Yes. Okay. So I'll start. Yeah. So thank you everyone for having me today in the meetup. Sorry, unfortunately, I couldn't make it to the meetup in person, but I hope this online would be okay. Yeah. So today I will be talking about how we kind of re-implemented the stream spec in Servo without the built-in SpiderMonkey implementation. Small introduction about me. I'm Taym. I'm a Rust system engineer, and my free time I contribute to Servo browser engine. Taym95 is my GitHub username. So small introduction about Servo. So what's Servo? So Servo is an open source browser engine written fully in Rust. So as it was mentioned, so Servo is one of the oldest major Rust project, basically because Servo and Rust were both created by Mozilla, so they need a project where they can prove the language and creating a new web engine, because web engines are complex. It can really help shape the project. Servo is built around the safety, parallelism, and compatibility, and it basically includes its own layout, its own rendering, so it does not reuse any layout or rendering from other major processors. So why I would want to talk about stream today. So basically, streams are quite important in a web engine. They are usually mostly commonly used in fetch. So basically, all the fetching of the asset or any network goes through the fetch, and all these need to be need to go under the hood using the streams, upload and download, compression, and media pipeline, and all the service workers. But so what was the problem in the old stream implementation? So old stream implementation in Servo was using built-in SpiderMonkey stream. So okay, what's SpiderMonkey? SpiderMonkey is the JavaScript engine used in Firefox, and we in Servo we have our own FFI wrapper because SpiderMonkey is written in C++. We have our own wrapper around this JavaScript engine written in Rust, and we have a crate for it called Moz.js. And this Moz.js was also given us the stream implementation that was coming from the JavaScript engine. But what happened is that in the recent SpiderMonkey releases, they actually removed the stream implementation from the engine, and they moved it to the Firefox itself. So because the stream implementation does not belong to the JavaScript language, so they moved it out of the JavaScript engine. And this caused a problem in Servo because Servo was relying on this implementation to make fetch work in the web engine, and for us, we need to keep updating the new SpiderMonkey version. When there is a new SpiderMonkey version, we'll go and update our own Moz.js, which is the FFI wrapper. But this prevents us because the code that we rely on it is not there anymore. So as a short-term solution, what we did is that, okay, we said, let's check what were the code that was removed from SpiderMonkey, and we patch it inside our own fork. So just to keep the update going and also keep the stream implementation working. But this is really short term, because a long term we need to do something about it. So basically what we said, okay, we need to implement our own stream implementation, and this time it needs to be pure in Rust, and it does not rely on any external implementation. So like this, we can remove the code that we restored from SpiderMonkey, and we can update Servo with SpiderMonkey's version in Servo freely. So for that, we needed the plan. So we need to identify what was the implemented in Servo. So Servo, even though SpiderMonkey had all the stream implementation, Servo was not implementing all the stream. It was only implementing readable stream. So for us to make this working, we created a plan. So we created an intermediate branch, and we kept merging PR to that branch until we reached the same amount of tests that were passing before with the old implementation. So as a result, we kept implementing. So as a result, we implemented readable stream, and we implemented a default reader and default controller. And when we merged this PR, we were able to basically remove the old code that we restored from SpiderMonkey, and we could freely upgrade the new version. But what does this means for like as an architecture in Servo? So if you look here, this is the old code that was removed. This is the new code that was added. And there is a function called read a chunk. So basically, you are trying to read a chunk from the readable stream default reader. So the function was unsafe, and it was calling an unsafe function directly to the JavaScript engine. So basically, this function was what was inside SpiderMonkey, and this is an FFI wrapper to the function, so we call it directly. And we moved from this implementation to a pure Rust implementation. So basically this implementation is just a pure Rust implementation. You have a match here, you have a type of reader, you have a default or byte reader, and you call a function read. So like this, it was even for us like in this way, it was even for us easier to debug, because now you are just dealing with Rust code. You don't rely on the JavaScript implementation. But we still need the JavaScript engine to pass like JavaScript objects. So basically, if you create an object in JavaScript, you still need to get the handler in Rust and doing the other way around. But the implementation is purely in Rust. Yeah, this helped us to basically remove some unsafe code from the Steam implementation. Yeah. Okay, so when we implemented the readable stream default reader and default controller, we needed to move on to the so in stream there is two there is a like default reader and default controller, and there is also a readable byte stream controller. So this one, it was a little bit hard, because when you work with the byte stream, you need to like manipulate the buffers, and when you manipulate buffer, you need to call call the JavaScript engine functions. So we wanted to avoid to go back to the same old implementation where we have like unsafe code inside our stream implementation. So we moved to something like this. So we created something called buffer source, and inside this buffer source, so basically as Rust developer, you would just call a function called detach, and you don't care what is happening inside. So basically here we are calling all these JavaScript engine functions. So we started noticing something when we moved all these implementation to a file called byte source.rs. We noticed that we are actually following the spec. So spec already was asking to have this abstraction, because later we noticed also that all these JavaScript engine, they all have the same functions under the hood. So this is Moj.js calling SpiderMonkey API. So there is a function called here detach array buffer, which is a function from Rust to JavaScript engine SpiderMonkey. There's another create called Rust v8, which is calling the v8 API, and it kind of has the same function, also unsafe function called v8 array buffer detach. And when we notice is that, okay, if we keep creating all this abstraction and moving all this unsafe code and all this JavaScript engine related code to an abstraction, we may end up in one of the situation when Servo can actually run multiple engines. So you can just start a Servo and say, okay, for example, I want a V8, or I want SpiderMonkey, or I want another JavaScript engine. That's what something we've noticed. Okay, so when we finish the readable stream, now we're not dealing with JavaScript engine. Everything is in Rust. So moving on with the streams implementation, it becomes much easier. So we noticed, okay, we have readable stream, it's purely Rust. We can actually just move on and implement writable stream, transformable stream, and all the other streams. So we ended up implementing writable stream, transformable stream. So because now we are just looking in the spec, and we write pure Rust code, and we only let the engine handle the values. Okay, so now when we've implemented the stream, we actually noticed that, okay, the abort controller, so abort controller is another JavaScript engine, abort signal. It becomes kind of mandatory to implement because the writable stream was relying on it. So we also implemented abort control, and all these changes of implementation, it become easier because we kind of moved on from the engine to our own Rust implementation. All these APIs become easier, and we started noticing something interesting because new contributors were trying to join, and they were just picking JavaScript API. So, for example, somebody from the community just picked up the compression API. And the compression API, it used the stream inside, For the community, it looks just some Rust code. I read the spec, I understood it, and then I can just implement Rust without caring about the engine. And more of the community started also to implement it. So there is another community member who implemented text encoder stream and text decoder stream. Yeah. So all these implementation, I want to know, okay, how Servo is doing comparing to the older engine. So in the stream implementation, actually Servo is doing quite well comparing to Chrome and Firefox and Safari. We pass almost all the tests. But there is a small missing field that I'm hiding here. The green is what is passing, and this one, I'm hiding it for a purpose, because all these failing stream implementation, they are not stream implementation failure, but it's the context that is missing. So in Servo, we are missing the shared worker, dedicated worker, and the service worker, which means when you execute stream inside this context, they will fail. But once we have this worker implemented, the stream implementation will just follow. It will just pass. Something nice about the future work of Servo. We already start working on the shared worker, which means we'll push the WPT, the test suite higher. Okay, so all this talk, it's technically it's good, but what does it mean for a Servo user? Like, what did we unlock? So we started noticing that when we implemented the whole stream implementation, also added a board controller. Previously, a Servo was not able to render GitHub. So now we noticed, okay, we're able actually to contribute to Servo using Servo. So we can just open PRs using Servo from Servo. I have some. So this is actually, I'm doing the talk in Servo. So the talk was in Servo. I'm just opening GitHub here. So you can see that this is the PRs. I'm logged in. And you can also see a diff if it's possible. So you can just go here and new browser diff. So all these stream implementation actually make Servo reusable for example for GitHub and also for this code. Yeah, so I showed the demo. Another nice example is that we were not able to run the ChatGPT in Servo, and when we were trying to debug it, okay, why this is happening, we noticed that one of the implementation of one of the cloning the request in fetch was implemented was wrongly implemented because it was not following the spec correctly, because the readable stream tree algorithm was missing. And when we implemented it and followed the spec and we pushed it, we noticed that, okay, at least ChatGPT now, the website is rendering in Servo. Yeah, that was kind of the idea of the talk. Yeah, contributing to Servo is fun. If you are interested, just reach out. We have the Zulip chat, and we have also starter.servo.org, where you can see some starter issues. Yeah, thank you.
Okay. My question is the overall plan to replace all instances of C++ in Servo with pure Rust? And if so, will like the idea be like you could replace SpiderMonkey with V8 or JavaScript core or whatever JavaScript framework you want? And does that include libraries like RTC?
Yes. So the idea is that we want to keep the JavaScript engine to do only the handling of JS value and object. We don't want to have like a JavaScript engine calls inside Servo, because this will tie us more and more to SpiderMonkey, and we don't want to do this because we want to make Servo as like an embeddable web engine, which means you can, if you want to add a support for another engine, this is the abstraction that we have. You just need to make your JavaScript engine expose these functions, and you can implement it. You might understand that why it was done like this in the beginning, because in the beginning they just want something to work, so they just hooked up Servo with the SpiderMonkey and they use the streams. We want to move on. So you mentioned example WebRTC. We want to move on from all the built-in JavaScript engine implementation. So if you open Servo in the future, you will have like a Rust code that's only following the spec. You can even like open the link of spec, read the spec, read the example, the fetch algorithm. You can see, you can debug your Rust code. The only moment when you need to move on to the JavaScript side is when you are exchanging example values, or example you're exchanging a promise or something. That's the only way we want it. And we are working toward this because we want to have Servo to give people ability to actually use another JavaScript engine. Example, one of the nicest things to have is to actually have a pure Rust JavaScript engine running in Servo. And to do this, you need to clean up the Servo implementation from all these built-in JS engine functions. Yes.
Hi, so I've used to be a JavaScript engine hacker. I'm curious, the different JS engines have very different memory models, especially around the heap. For example, V8 has its isolates, its SMIs, JSC has its conservative collector. Tell me a bit about the abstractions you use to support these different memory models. For example, how do you expose your objects so they can be discovered by the different GCs in an abstract way?
So yeah, that's a really interesting question. So basically now we are not doing anything about this yet, because what we had like Servo that has Java SpiderMonkey called inside the DOM implementation. What we are doing now is we are just cleaning them up. So cleaning them up, the Servo implementation is still kind of tied to the GC of how the SpiderMonkey triggered the garbage collector. This will be our next step, where how can we example, we're looking at how example the JavaScript core, the JavaScript engine running in WebKit, how it does the GC, and we're trying to match it to what we have in Moj.js, and because we cannot have like a big bang implementation, we're trying to kind of find an intermediate state where the two JavaScript engine we want to kind of match them how the GC works. This is still not done. For now, we are in a situation where we're just cleaning up all these in Servo calls, but this will be next step, and it will be quite big implementation.
Cool, thanks. I'm wondering, have there been any bugs in other browsers that weren't found in Servo among what's been implemented so far? And if that hasn't happened yet, do you have a kind of timeline until something like that happens?
So there is a lot of bugs that we noticed. They are mostly about the memory management, because of how Rust does the memory management and how we integrate with the other JavaScript engine. So I had a colleague, he gave the talk in Rust Week this week about founding an undefined behavior in Servo. So basically, we rely on JavaScript engine Moj.js, where we do some unsafe code. So in language like C and C++, these behavior, you can easily misuse them. But in Rust, we see that, okay, when we try to bypass the memory management in Rust, we kind of end up in a lot of crashes. So we only see these kind of undefined behavior when it's around memory management, but we don't see all. We're still not in a point where we can clearly say, okay, Servo is clearly better in this area yet.
All right. I think that was all the questions that we have time for. Thanks a lot, Taym. It was a pleasure having you here, and thanks a lot for your dedication. I know it's very late. I believe it's past midnight your time. So thanks a lot. Let's give a round of applause for Taym, please. All right, and so our next speaker tonight is Ellie Huxtable. She is the creator of Atuin. I believe I'm hoping I pronounced it correctly. And let's give a round of applause for Ellie.
So, hi, my name's Ellie. I'm the founder and maintainer of Atuin, and today I'll be talking to you about syncing a ton of bash. So first of all, a little bit more about me. I've been working in infrastructure for a long time, previously at PostHog and Coinbase and a few others. I've been writing Rust for even longer, since like 2017 or something. I've loved that thing. But lately I've been writing a little bit more Elixir, and I'll be mentioning that all to you later because where else to talk about Elixir than a Rust meetup? Last year I moved to San Francisco from London, so it's been kind of nice to get to know some more people in the Rust community too. Other way around. Firstly, what is Atuin? So at its core, it is a shell plugin that starts to record all of your command history and all of the context around it. So like what directory the command ran in, whether it exited successfully, like all of that kind of context. We take that information, we send it into a SQLite database, and then we present, if you can see right there, a fuzzy search TUI on top of it. So it replaces all of your control R and up arrow and all that stuff. Didn't really stop there. We built a sync algorithm on top of that, which is the whole topic of this talk. And that basically means you can sign into an account and have the same shell history everywhere forever. We have some users that have many, many years worth of shell history that they're syncing. We have built a few other things lately too. So we also have a PTY proxy. Like, hands up if you know what a pseudo terminal is. Just want to kind of gauge. Okay, cool. That's a decent number. Basically, what this allows us to do is render things on top of other things without using an alt screen or clearing space, which was really fun to hack around on. And it also gives us the possibility of recording command output in the future, as well as just the command itself. We've also got an AI integration, which basically allows you to have help in the terminal that has the context of all of the stuff you've done in the past and to help you figure out what to do next. Next up, though, before we talk about how the sync works, let's just sort of go into the actual constraints and requirements we have. First of all, it has to be end-to-end encrypted. Shell history shouldn't have AWS keys in it, but it probably does. It has to be offline first because in our system, devices could go offline for a couple of months. You can't have a dependency on an internet connection to search your shell history either. That would be super weird. It also has to support multi-device sync. We have some users with like hundreds of machines syncing. People use them in sandboxes and ephemeral VMs and all that kind of stuff. And we also look at this as a very append-heavy workload where typically people are appending to our sync system more often than they're downloading. So let's cover Sync v1. This one sucked, to be honest. It was designed just for me, and it worked in a very naive way. So if you were to have a very like v0, spend half an hour building sync, you might look at it like this, where the client would look at how many rows it had, and it would ask the server how many rows it had, and it would just upload and download stuff in a loop until the two matched. And this actually worked for a surprisingly long time. It did start to have some problems. You can kind of look at the database queries as like count star locally, count star remotely, and then just spam queries until it works. Some of you might have guessed count star is really slow, especially when you start to have like millions of rows remotely. It really doesn't hold up all that great. You end up like scanning the table way more than you'd like, and it really sucks. There was also a bunch of consistency issues where people would report that sync wouldn't work until they ran the command like 5 times, which is really not the experience we wanted them to have. And it also only encrypted data at sync time. So before uploading, we'd encrypt a record, upload it, and then after downloading, we'd decrypt it and insert it, which sounds reasonable until you consider that we leave key management up to the user, and the user screws that up, and that's very understandable. It's a hard thing to do. But it meant that the remote store would end up with like mixed encrypted data that you couldn't download because it had the wrong key, and it was all kind of a nightmare. It also wasn't generalizable, so we put a ton of effort into syncing text around, and it only synced shell history, which is our main thing, but there's a ton of other stuff we can do too. So introducing Sync v2, which is the one that pretty much everybody uses now. We actually switched off Sync v1 like 2 years ago. Sync v2 solves a bunch of those issues. We have a local record store. So what this is it's essentially a copy of everything in the remote database. It stores it encrypted locally. And then we basically use this store to process and turn it into the actual database that you search. It handles small blob sync. It doesn't really care what the data is, so long as it's not too large, and usually can be represented as text. It's modeled as an append-only log. Well, it's actually modeled as many append-only logs. So each machine gets its own little log that it can write to, and it gets one of these per data type that it syncs. So you can imagine one laptop will have one log for shell history, one for scripts, because we also support syncing scripts and a few other things. And this is really nice because each machine can do whatever it wants to its own little log, and nobody else is going to trample over its data. This is also modeled to be eventually consistent. I always struggle to explain this without saying eventually, so I'm going to assume you'll know what it means. But syncing happens whenever, and over a period of time, it will converge. So sync v2 is built in 2 steps. First of all, we have the sync step. What that does is, you can see at the top, we have all of the data, and it builds a little summary of what your local store looks like. The client calculates what we call its own sync heads, and then it asks the server to calculate its version of this data structure, and then the client can compare the two and figure out where it's ahead, where the server's behind, and what needs doing. We then use this diff to do like a very minimal set of operations to make sure that all of the data we're supposed to have is where it's supposed to be. I'm highlighting the database queries because it's slightly foreshadowing, but we went from the count query to a max and a group by, which is still way better than a count, but like we just hit nearly 600 million rows, and that doesn't really work anymore. More on that later. After you sync the data, you have to build it. And what this means is we take our log of encrypted records, we decrypt and deserialize them. In the case of history, this is turning it into events. So an event is create history or delete history. We sort of collapse all of those events up into a list of commands and then insert them into SQLite. This process is actually really great because we can change SQLite schema whenever we want to. We could even swap it out for a different database entirely. And all we'd have to do is change the last bit of the build process, and you can just regenerate the database whenever you want to, which is really nice because some users like to poke around in the end result and break things. So it lets them recover that too. So what v2 unlocked is, first of all, we can sync more things. We use it for syncing shell scripts, dot files. So we've actually got like a little key value store sync. You can just sync random little blobs of text if you want to. It has no issues with many devices. I'm always surprised by some of the numbers people get to. It's also possible to rekey your store. So if you mess up and put the wrong encryption key in somewhere, it's possible to change that key, or if you accidentally leak it, you can roll the key in the future as well. It's still not the easiest process. I would like that to be much easier, but we're getting there with that. It's also way faster. So with Sync v1, we would end up with people uploading and downloading way more data than they needed to get to the point where everything's consistent. And with v2, it almost always just works this time. Nothing is without trade-offs. First of all, we're storing a local encrypted copy of all of your data and the materialized database at the end as well. So that means we've got at least double the disk usage on your machine, which kind of sucks. The build process I just told you was amazing is actually slightly more complicated than we'd like. And if you screw it up, it can mean that different machines end up with a different view of the data. This is essentially an unbounded log as well. So over time, like several years, but over time, it just gets larger and larger and larger, which isn't ideal. And also the sync performance. I mentioned the group buys earlier, and much as they got us to where we are now, they're not so great anymore. So naturally, I reached for an entire rewrite as the solution to all of this. And it's a bit of a longer story, but we were playing around with Elixir for some stuff anyway, and it ended up to be a really nice fit for what we're doing. If you haven't checked it out, or if you don't know what the beam is, I'm just gonna summarize that a little bit too. It was originally designed for telecom usage by Ericsson in the late 90s, and it's the VM that Erlang runs on. It handles many processes, so if you think that Go handles a lot of processes, Elixir is way more than that, or the beam is. It has a lot of clustering primitives that make horizontal scaling very, very trivial, and has really nice web frameworks, and it's all generally pretty great. And if you don't give it a try after this, at the very least, please watch the Erlang movie. It's on YouTube, and it's really funny. What this brought us is a bunch of wins. So firstly, we now have a single sync process on the server for every single user that is syncing with our database. This is partially a simplification for our implementation, but it makes a bunch of race conditions kind of vanish. It makes things easier to reason about. When all of your operations are serialized, like things just work a little bit better. In-memory caching is really trivial. We have one process that all requests go to, so we can cache things in memory right there without Redis, and it mostly just works great. We definitely could have built this in Rust, but Elixir and the Beam in general has a bunch of things just out of the box that made it so much easier. There's a graph, if you like graphs. Our P99 latency on the sync heads comparison endpoint went from pretty bad to more or less 10 milliseconds flat across the board. So what's next? We have a bunch of other problems other than performance. We want to stop that unbounded log growth, so we're looking at building snapshots into the protocol where maybe every 1,000 records or something like that, we take a snapshot. We can upload that to an object store, which avoids having to page through Postgres for all of our downloads. The really cool thing about snapshots is you can compress them. If you tried to compress one bash command, it's probably going to end up larger than what you put in. However, if you compress 1,000 of them all at the same time, you get some really nice compression ratios. This also paves the way for larger records. I mentioned earlier that the PTY proxy enables us to store command outputs as well, which is obviously way larger than the command itself. So we need to figure out a way for storing that too. So yeah, there's a lot of really exciting things to work on next. So we are actually hiring. And if anybody wants to come and work on Rust and terminals and all that good stuff, please reach out to my email, say hi after this, and then check out the website. But there, if there's any questions.
Hi. I've used Atuin for years, so thank you so much. I've always been very interested in the economics because I think you work on this full time, correct?
Uh-huh.
Yeah. And you have for some years, right?
Yes.
So I've always been interested in the economics of how do you make that work for a terminal tool that's very useful, but I feel like from my perspective, it would be hard to monetize.
So for a while, I just ran it out of my pocket. It was really cheap to run for a really long time. Lately, we are in San Francisco, so I raised some money to build this into something bigger, but that's the answer for now.
So first of all, I'm a happy user of Atuin myself, so thank you, and I guess the rest of the people who have worked on it. So with regard to Erlang, Elixir, that ecosystem, I've looked into that a little bit. It does seem like an interesting software ecosystem. The big thing that puts me off of it is that it seems like it comes out of the dynamically typed 90s tradition. So I do wonder, what's the type story there today?
Yeah, that part sucks. So basically, Erlang, I never wanted to learn because it's really ugly. Sorry if there's any fans here. Elixir is if someone looked at Ruby and then was okay, we're going to get rid of all of those mistakes and make it better. There's a lot of pattern matching in there that makes things really nice. It can help avoid a lot of the mistakes that type systems can also help you avoid. There is a type checker in it. I haven't used it a bunch. It's an opt-in kind of Python style thing, I guess. But there's also Gleam now, which I'm super excited about. Gleam is awesome. Someone light up when I said Gleam. It's basically it's definitely been influenced by Rust. You should check it out. It's got it's written in Rust. It runs on the Beam, and it's got a nice type system and all that. It's worth a look.
Thank you so much for the talk. Big fans of Elixir and Gleam and the entire ecosystem over there. Great folks. What would you say that Rust could learn from Elixir? And specifically, I'm thinking can somebody add a feature to Tokyo and make it real good in an Erlang way or something? What can we bring from there to here?
I think I saw a couple of people try this because there's definitely a lot of Elixir fans in the Rust world, but there's I think the clustering is really cool, and it's sort of taken out a ton of work that we would have to do. For anyone that doesn't know, basically you can take a bunch of machines that run the Erlang VM and you can connect them up, and then anything on one machine can address something on another machine, and it's really neat to work with. And that's what we use to have one global process per user that can migrate and all this stuff. It's really cool. It's very hard to implement otherwise. You'd probably fall back on something like Redis or some stuff like that. And if Tokyo could do that out of the box, that would be awesome. I think it's very unlikely to happen, but it would be really cool.
I was just curious about the algorithm that you use to ensure eventual consistency. So like if I have two clients that are both offline, they run a bunch of commands and then they sync, you know, will there be like interleaving between the like different commands that were run? Like, does it matter? Like what is even like the correct intention preservation that you're like trying to achieve?
Sure. So there's a few things we had in mind when we built that. Firstly, we're really lucky that it's not like text editing or something where the edits really depend on it. Yeah, I could talk to you afterwards about another project we were looking at like text editing sync and it really sucked. But no, we're lucky that things don't tend to depend on each other. The core design sort of pattern we followed is that the state should always be the same on every machine when it's resolved, even if that's wrong. So long as it's consistently wrong, the user can then go ahead and correct that, and then that should propagate across the system. So first of all, we usually just use a timestamp to try and make sure like which thing happened first, make sure a delete follows a create.
Like an actual timestamp or like a lamp?
Regular timestamp, yeah. And then any conflicts we have, we just use like a hash function and decide which one wins. And so far, it's been great. I'd like to improve it, but no one's had any issues.
Is there a network time?
Yeah, exactly. We don't really have anything that depends on anything else. So they're pretty isolated.
All right. Well, thank you, Ellie.
Thank you.
All right. So our third speaker is Eric Holz, who works at Z Industries. And let's give a round of applause for Eric.
So, hi everyone. I'm really happy to be able to talk to you. The title of my talk is Durable Rust in the Age of Agents, or How We Learn to Stop Vibe Coding and Build Stone. We'll explain a little more what that means as we get into it. But I want to talk a little bit about the title. So the first part of this is durable Rust. And so by that, I mean code that lasts. Actually, I want to go back to show this picture here is one. So at Zed, we get to do an annual summit where we pick a cool place in the world to go, and the whole company gets together and we all meet each other in person. This year was in Rome, and this is a picture I took while I was in Rome. And what I like about it is you can just see the layers of history in here. So the street down here at the bottom is like from 2,000 or more years ago. You've got stuff from like the Middle Ages. You've got, I think this is a castle that some person built on top of ruins of a wall back in like the 1500s, and then you've got kind of more modern stuff in there. And it's just, you have all these layers on here. And I was looking at this and I thought this is a really great metaphor for software and the way that software kind of develops and evolves over time. And so that's what I mean when talking about durable Rust. So looking at how we can use the features that are not necessarily unique to Rust, but sort of all come together uniquely in Rust, and use that to make software that's going to last as long as some of those ancient Roman ruins. So that's kind of the idea for that. And then this Age of Agent parts, at Zed, we are doing a lot of agentic coding now. And so that has inspired a lot of my kind of experiences recently. But one of the things I realized as I was working on this talk, this is especially for the people in the audience who may be a little more AI skeptical, that really this talk is about good software engineering. And the things that I'm talking about are things that I realized I've sort of learned over my career and have just been maybe sharpened or become much more important in the last few months as the industry has just been changing so fast. So just wanted to comment on that. To my sort of career compressed into 2 bullet points here. As you know, I'm currently working as Zed. And I also wanted to mention, like, I love Rust. I've been a contributor actually till like 15 years this month, like almost to the day. So come talk to me afterwards if you want to hear early stories about Rust. I love talking about that kind of stuff. It was a very different language back then than it is now. So, but I think now it's been long enough that I can just say even longer ago that I've been programming. So I started learning how to program as a kid. I imagine many of you did as well. And so I did want to show you one of the first programs that I ever wrote. I managed to find this buried in my mom's house somewhere a long time ago. I didn't get it running, so I was hoping to actually show screenshots or a demo of it. But this is me as a child, made an animation program where you drew stuff in MS Paint and animated it for people, and made a really official looking disk that I thought maybe I'd sell it as like shareware over the mail or something like that. I never did, but anyway, sadly I've lost the source code for this. But if you imagine if I can, from what I can kind of remember, it probably looked something like this. So this is Visual Basic. It took me an embarrassingly long time to learn about arrays. And so I remember writing a lot of code where it's like frame 1, frame 2, frame 15, and then a bunch of like, okay, if current frame is 1, then show the first picture. There's actually a typo there. It should be image 2 on the second. Anyway, it was not good code. There's a ton of repetition. There's a ton of abstraction, and there's no abstraction, not a ton of abstraction, the opposite of that. And like no encapsulation to speak of it. So why am I showing this to you? Why are we laughing at Eric as, a kid not knowing anything about programming? The reason is that I've realized there's a lot of parallels to this in the code that I see come out of agents a lot of times where, so as a kid, I didn't have a lot of software engineering expertise and experience, but I could compensate for that with a whole lot of free time. So I had the time to go and type all of those things, and with agents, it's kind of like that too. They haven't had to maintain the code that they've written for 15 years at this point, and they can spew out tokens just incredibly fast. So when I look at the code they write, I see them, duplicating lots of things when maybe you should factor it into a function. I see them making tons and tons of fields when maybe we should combine that into some object that keeps the semantics of that all together. A lot of these things that we learn through the course of our career in maintaining software over a period of a time. So to get into Zed and kind of lessons we've learned recently, I want to jump over to this. Is that font okay for everyone? I can make it a little bigger. That's probably better. So with Zed, we just recently shipped a feature called Parallel Agents. So it added the sidebar over here, where you can now have many different threads working in parallel. I'm imbuing them to be a slideshow today, so I've made a thread for each slide that I want to show you. So you can use any tool wrongly enough, I guess. So in the code for the sidebar, we had this function in here that has been kind of the bane of my existence for a while, called rebuild contents. It's a good function, but it's long, it's very complex, and it's one that I've had to spend a lot of time working on. Michaela too, as you can tell from the blame in there. So Michaela's in the back, you can wave at her. And anyway, so this is code from a while ago. It says 2 months ago, it feels older than that. But this is the code that goes and finds everything that shows up in your sidebar. And in the first version of it, which we have up here, it was pretty simple. If I collapse it, it's, a little over 200 lines of code, a little long for my taste, but it's pretty reasonable scrolling through here. And what this is doing is basically just looking at what workspaces you have open in Zed. So we introduced this idea of a multi-workspace, and we add an entry of for each of those in the sidebar. So small, manageable, but we didn't know what we wanted the end product to be like, and so we had to do a lot of iteration and a lot of let's combine this, let's fold this thing in. And we started adding more and more functionality into it. And so one of those things was we added this notion of work trees. So I'm using that actually really heavily here because I made a different work tree for each slide that I'm showing. So, we add a little bit more to the code because now this rebuild contents, we have the workspaces and we have the work trees, and we've got to do some extra work with that. Now it's grown to closer to 400 lines of code. So it's getting bigger. And what I should say is this was for us kind of an experiment with really pushing agentic coding pretty far. So we started out with a big specification for here's what we want this to do. Here's the performance, the algorithmic performance requirements we want to hit. Here's a really extensive test suite that should always pass. And agent go wild at it. And what it came up with at first was pretty good. But over time it started to grow and get bigger and bigger. Eventually we had to add this notion, the agent I think came up with this, of absorbing threads. So it's you go through these threads and we need to absorb it into this other category in the sidebar. And if you look at this code, there's 4 hash maps in it, all in a row, and we've got a loop. I think at one point this loop was quadruply nested. Oh yeah, it is. Here we go. 4, 4, 4, 4. You know, this is, I think, around the time that I got involved in this project, and I was like, I cannot fit this function in my head anymore. So I spent a few days, I think, pairing with Michaela for a lot of this, but oh yeah, we're up to like over 500 lines of code now, so it's growing and growing. I spent a few days then trying to make sense of this, and somehow this was in my Git history somewhere, of me trying to say, hey, let's have this idea of like a project group and really treat this as like this first class citizen. We want to map threads onto their headings, and yeah, so I wrote up like these like pseudocode comments in here for here's what we need to do, and like, oh, there's, you know, whatever. So trying to make sense of this so I can build the right abstraction to keep this function manageable, because it was clear at this point we're going to have to keep building on it and iterating on it. And so what I came up with is then, oh yeah, we can document, you know, we want to single forward pass over the workspaces and threads, and then O T-log T sort, and avoid extra things, extra scans over the data. We wrote down some properties up ahead of there. So that's documentation that's helpful for humans, but also helpful for the agents that we're working on this code. So then those 4 hash maps are gone. Like, trust me, I guess that we have one, I guess, a hash set. But now we have this thing called a project group builder, which I added over here, which treats the name of the, like, we're sorting these threads into project groups. We have a type that represents the name, that becomes the key in there. We've got this nice little component that is responsible for building and keeping track of these things. And so, you know, we got there, that was a step forward. And then we decided to rip it out because it still wasn't quite fitting together. And so this one here, yeah, we've moved this to the multi-workspace. Now it has this idea of a project group key, but this component that is responsible, like the multi-workspace still is not quite managing this well. It's more just still recovering this from ambient state, which was the thing we were trying to solve with Project Group Builder. So anyway, it was just a lot of iteration in here. And then eventually we realized, hey, we do need this concept of a project group builder. Like, you know, we built sort of the same data structure under a different name, and really made these things like these project groups a first class concept that is tracked by what we call the multi-workspace in Zed. And then landed on pretty close to what our version is now that ships. So that's a quick tour. Well, hopefully it was quick. Tour of the history of this one little, you know, the sidebar. I'm pointing on my screen. It's the sidebar over there. Yeah, just all of the iteration we went through to get this out and to get something that we were happy with, and also to get something that's robust enough that we can keep building on it and that we can keep sending our agents out to build on as well. So with that in mind, I realized through this process that I had this agentic workflow that I end up using, which has these 2 phases. The first one is this building phase. And this analogy that I came up with is that it's kind of like building a sandcastle. Like, you're building it out of sand and you're building it out of wet sand, and you can build really fast. Like, you go out there in a couple of hours on the beach and you put all this stuff together, and look, it's really ornate and nice. There's a person in the water for some reason, but yeah, very, very detailed, really impressive. You could go show someone a really impressive demo of like, look at our building skills, you know. But before long, sandcastles start to look more like this, where it's been kind of crumbled up. You know, it's eroding away a little bit. You still can see kind of some of the structure, but it's not really holding its own weight. And that's one of the things about sand, is as you pile more and more of it up there, it sort of crumbles and decays like we have here. And so I realized during this building phase, which I tend to do by kind of prompting the agent and saying, hey, go out and implement this feature for me. It comes up with something that looks good, but also I had the sense that like entropy is increasing the whole time there. It's like I am losing the ability to understand what's happening in this code. And so I have to go to this next phase, which is refinement. And so to stick with our castles analogy, the idea is we're trying to decrease the entropy, and you turn that sandcastle that we had before into something like this that's gonna last for a long time. You we're building out of these durable materials. So this is where the stone from my subtitle at the original or at the beginning of the talk comes in. That we're building out of stone. We've got these nice structures. We've got this foundation. You can build on top of it. It's going to last there for a while. And then once you have that in place, you can go back and build some more. So during this refinement phase, we sort of take all of that entropy that we had before, lower that down, build structures that we can reason about that hold it together, and lower it down. And then we can go back and we can build some more. And then we'll, in the course of doing that, we increase the entropy again, and we got to go back and refine it. And it just, this is what I do now, go in circles like that. So let's get into some Rust now. I'm going to close out the talk with 3 kind of lessons that I've learned. Probably if you've been writing Rust for a while, these will probably not be super surprising to you, but I will share them anyway. These are some things that I've found myself using when I feel like I'm writing really Rust code that I'm proud of. These are the kinds of things I like to try and do. So I think this big one is making invalid states unrepresentable. So how you do that in practice is using the new type pattern where you wrap some data type in a struct. And what you're doing by wrapping it in a struct is you're attaching some extra meaning to it, some extra semantics. And then you can rely on those later when you're reasoning about your program. And then also I like using enums instead of flags. So, you could have a struct with 10 Booleans on there for which state are you in right now. And agents seem to like to write code like that, probably because they're trained on a lot of code that does not have enums in it, like Rust does. And so this ends up with, at some point you'll write this in your program. This will never happen. And I would say that should never happen. When you get to the point where you write this should never happen in your program, that's probably a sign that there is a more precise abstraction you can build that will fix it. So let's look at some code to kind of put this into practice. Let's say we have this imaginary job runner. We have a jobs, which is a vector of the jobs. We keep the current one as a usize, so that's an index into it. We have started and finished. So it's 2 Booleans there. So we've now got 4 states. But one of them where, a job that is finished but not started should never happen, So now we've gotten in the state that doesn't make any sense to us. And also, we don't have anything to guarantee that the current index field, actually is in bounds for there. So we've got to keep bounds checking every time we do it and all that. So we could rewrite it more like this. This is not exactly perfect, but hopefully it gets the idea across. So I've added this new type, this job index around the size there, where I'm saying, hey, this usize isn't just some random number. This is meant to be an index into that jobs array. So, and then we can, in the constructor, make sure that we do that bounds check. So then you can just kind of rely on the fact that it's in bounds. And Rust will still insert the bounds check. I would probably argue that you shouldn't go out of your way to get rid of that. But even in reasoning about it yourself, that's a big help. And then the other thing is we've replaced the state on it, those state fields, with now we have an enum. So it can be pending. We haven't started running any jobs. Running, we're running a certain job, and then when we're finished, it's all done. And so then in your match statement down there, it's, that panic is gone because there's not even a way you could write that block of code, like the if statement that leads to where this should not happen, because our data completely describes all of the possible states that we care about and none of the extra ones, which helps you build robust code. So then if you can't represent any invalid states, the next thing you should do is handle all of the cases, because you've just gotten rid of everything that's invalid. So the only thing that's left is valid, and it's all stuff you should be dealing with. One of the things I find with that is using underscore in match, which if you noticed, I did that in the last slide. We should use that sparingly. So here it is where I've expanded the match down at the bottom. The reason I like to do that is at some point you end up adding an extra field or an extra variant to your enum. And then I've introduced so many bugs where if I needed to handle it, but there was a catch-all pattern on it and I missed it until, my code went wrong. So this way you get a compiler error if you don't handle it, and it forces you to go through and make sure that you keep it all up to date. So, and then finally, I've talked a lot about abstractions and invariants. So we should define those clearly and protect them. And Rust has some tools to help you do this. The last bullet point there is kind of new. I'm a little unsure about it, but I'd love to hear what people think about that. So one is really like lean into these some modules and use that to protect visibility. So you know, if you have these invariants about your program, like things that you assume about the way your data is set up, keep those packaged inside a module so that, and then be really, really careful about your public interface, so that way no one else can violate it. You know, you can rely on those because all of the code that is responsible for defending that invariant is in one place, and you can see it all at once. One of the things I've noticed is agents like to erode these boundaries. So you write this really nice abstraction and you're like, oh, let's just add a pub accessor to this like internal field in there because that'll make my job easier. So watch out for that. So this bullet point down there getting to it is then, in Rust, the convention is to put tests kind of as a submodule of the thing you're testing. I like that because it keeps your tests really close by. Makes it like kind of a joy to write tests. I write way more tests in Rust than I do in any other language. But I think especially now that I'm starting to use agents more in developing my test suite, I actually think it's better to move the test to a sibling module. And the reason is that then your test can't see any of the internal details of the thing that you're testing. And so one of the cases one of the things I like to do is if I get we get a panic in our telemetry and it's like, oh, I want to see what happens. I'll just give the agent the stack trace and say, hey, can you build a reproducer for this so that then I can repro it locally? And so what the agent loves to do is say, oh, this happens because you're in this invalid state. Let me just go construct that invalid state from scratch. And then look, it crashes. And it's like, well, of course it does. You built it invalidly, So what you want instead is to write your test so that you're using the public interface for the public API. And you want to see whether using things that you're exposing to your users, your clients of your library or your software, they can actually get into these invalid states that cause it to crash. So anyway, I'm trying this out now with some of the newer code I'm writing. I'll let you know how it works out. Feel free to try it too. Let me know how it works out. So those are my three bits of advice for writing durable Rust code. And I just want to close by saying, build with sand. It's okay to go really fast and, get something that's cool and quick and elaborate. You can try out the ideas. You can iterate a lot faster, but then you need to refine it into stone at the end. So it's worth it to take the time to do that because that's what lets you build and keep, build into the future and keep robustness into the future. All that. So that's my talk. Thank you.
Hi, loved your talk. I've been doing a lot of the same things. I'm curious if you have had any adventures with unsafe Rust and with like LLMs, and if you've had some experiences around that.
I used to write. It felt like almost exclusively unsafe Rust. Like back in the early days, like to do anything you had to write unsafe. Fortunately, I don't have to write much unsafe anymore. That's a good question about agents. I have noticed agents love to write safety comments, but I don't know that I believe most of the safety comments that they write. So watch those closely, I guess. I don't know, Miri's, I'm sure you know this, of course, but Miri's your friend when you can use it. But unfortunately, a lot of the times that you want to write Rust, it's because you're writing bindings to external code and Miri doesn't help you there. So I don't know. Maybe I'll start writing some unsafe code and try it out with agents. But yeah. Yeah, you've got the mic.
Yeah, I have a question. When in the early stages of Rust, one of my friends told me there was like it was garbage collected and it had green threads. I'm just curious why green threads were removed from the standard library.
Yeah, I wrote the green threads to start with, so I didn't remove them though. But yeah, so Rust. I'll touch on garbage collection first, but Rust was it never, as far as I know, never got a garbage collector. It was always planned to have a garbage collector. So early Rust had 4 different kinds of pointers. I remember someone saying, hey, the first thing you need to know about Rust is that it has 4 different kinds of pointers. And that's not, anyway. So what we call RC now used to be an at pointer, an at pointer. So you would, instead of like a asterisk for like a raw pointer, you would write an at symbol before your type. And then that says, oh, it's a shared pointer. Those shared pointers are supposed to be garbage collected. they kept saying, "Oh, we're going to write a garbage collector someday." And then I think after like 5 years of no one writing a garbage collector, we decided we didn't need one, and so we just stuck with RC. Green threads, why we got rid of them? A couple of reasons. They're hard to get right, especially when you want to do calls into C code. Because with green threads, what we had to do is keep really, really tiny stack slices, or stack, just stacks, your program stack. And then we did like a segmented stack. So you overrun that and you jump to another stack segment and then jump to another stack segment and so on. You can generate your Rust code so it handles that just fine. But C code is used to having like 8 megabyte stacks. And so to call into a seek function, you then have to keep a separate stack around for your C code and jump over to that and then come back. And then it's really annoying. Also, CPUs are really, really tuned to run code that behaves like C on the stack. And so when you jump between stack segments, your CPU gets really confused. So those are some of the reasons. It also just turned out that like threads on Linux are super, super cheap. They were basically as cheap as what we were getting at green threads anyway. So I think those are the main reasons why we just went with OS threads. Michaela.
Well, first off, thanks for the talk. So you have this nice process of like building out the sand, kind of getting the shape right, and then like solidifying into stone. But like, what's the transition point? Like, what's the critical point? Like, where do you go? Like, how do you know that it's time to start carving instead of stacking slop on slop?
Yeah. I think you can do this somewhat fractally. I'm kind of making this up as I go. So, when I'm doing everything really carefully, I like to do this kind of at a per PR level, where it's like, agent, go draft my PR, and then I go and read over it and make sure that I'm really happy with it. Sometimes I get kind of lazy about that. I think definitely when you get to the point where you feel like you're not able to make forward progress because you can't understand the code, or you've kind of like your code has gotten ahead of where you understand it, that's a good point to sort of take a step back and give your understanding a time to catch up. So I think it's good to sort of do it almost at like the end of each thread, where it's like, okay, I've got some chunk of work, let's go and kind of make sure we're happy with this. But sometimes you don't necessarily see the whole. I mean, we saw this with rebuild contents in the sidebar. You don't really know necessarily where you're going until you're a lot closer to it. And so you may have this bigger refinement phase at the end of a bunch of build phases. Oh. Okay, I guess the next over here. So
yeah, hi, my name is Marcus. Thanks for the talk. I really liked the portion where you kind of like form data structures in order to kind of better lend itself to be contextually like adaptable to an agent. I found myself doing a very similar thing, but I haven't gotten to the point where I've like made the data structures such that I don't have erroneous like states like you do. But I'm curious, is the agent adapting to that really well? Like, is it able to, like, if you have a new state that you're thinking of, like, is it able to expand and make that new state in a contextual way, the same way that you've written them previously, or does it have like trouble kind of doing that? Does that make sense?
I think so. I mean, one of the reasons encoding all this stuff into your types helps a lot is then the compiler kind of forces you to keep following those things, and so the agents are really good at like following compilers or fixing those. I do think that this is not like the natural way that the agents I've worked with like to code. I know I'm like anthropomorphizing them a lot, but they, so it does take this sort of constant vigilance. They like to, like I've said before, they like to tear down these boundaries and stuff that you build up. But they're usually pretty good if I say, hey, could we do an enum here instead of a struct with a bunch of fields? I think they're actually usually pretty good at once you point them in the right direction, they usually come out with, or in my experience, they come out with something that I'm pretty happy with. So I don't know, hopefully that addresses it. We should get you, Mike, because you've had your hand up for a while.
What's your favorite thing? What do you always have implemented from the early days of Bust?
Favorite thing, like proudest of having implemented from early days of Rust? Yeah. one of the things I thought was really cool is it got ripped out. So I was an intern for 2 years, 2 summers on the Rust project. As with most intern projects, this got ripped out kind of right afterwards. And with proc macros, we could do it again. I'd love to go back and do it again someday. But I added this thing called the protocol compiler, which was for I didn't know it at the time, but it was basically session types implemented as a macro in Rust. So for people that don't know session types, what that means is you could describe a state machine basically of so it's you're in the state, and then these transitions, which would be like messages. So it's okay, I'm in this state, you can think of it for a network protocol, and it's I send a login message, and then it can send back, so then I go into the state where I'm logging in, and then in logging in, you can have a message that's either maybe I receive a message that's a login result from the server, or it's login success or login failed. And if it's login success, you go here, and if it's you describe this whole state transition diagram for it. So then it would go and generate 2 different modules, a server side and a client side, with data types in there and functions and stuff, so that it encoded that whole state machine into the type system. So you couldn't send a message that the server wasn't expecting, and vice versa. And then that also let us, for certain protocols, pre-allocate all the space you could possibly need. So then a lot of the protocols became, because you can sort of prove that there's no way this protocol can have more than this much data in flight, and that let you do it as 0 cents. So that was I think the thing I had most fun with. The thing that has persisted the best, I was the first person who needed to share pointers between threads, so I wrote arc. The first one, it's been entirely rewritten since then. It shares no code with my first version. But
one pattern I've been using mainly for things I don't like writing UIs and TypeScript and stuff, is to get the API I want, and then rather than turn it into stone, just throw everything away and build it all again from scratch.
Yeah.
And so it's the building with sand faster. Is that valid, and when would you use one and not the other?
Yeah, I think I love it when you can write something and then throw it away, because you end up sort of discovering all the stuff. There's a lot of things you can't discover without just trying to do it, and when you sort of build it from the beginning, knowing all those things, then you get a lot from it.
You said AI is really good at burning tokens, so if I just build it, use it, expect from my API what doesn't work.
Yeah.
Throw it all away and just burn more tokens.
Yeah. I think I haven't done a few of the too many of that particular pattern yet, but I think I've gotten really close to it a couple of times, and I'll probably start doing more of it, where it's you have one thread where it's hey, let's just run through this feature for a while, iterate it on a bunch, then maybe end the thread with write me a design document for what we just did, and then go start a new thread and say, hey, read in that design document, and let's implement this for real now. I've got something I'm prototyping on my laptop that I hopefully we'll get to do that with, but we don't know yet. All right, thanks everyone. I'm around for more questions afterwards.
All right, thank you, Eric. All right, I think that concludes our planned part of the talks. So I just want to say thank you to all our amazing speakers who prepared these wonderful talks. And let's give a round of applause for our organizers. That includes Michaela, Rain, Tassif, Esther, Luna, who helped make this event possible. And once again, thank you to our generous sponsors, Zet and Root VC. So now we have time to mingle. Thank you. Thanks a lot for joining us tonight in person. And we have this space until around 8:30. All right. Thank you.